This video is about generating pulse width modulation signals from an audio input. It corresponds to section 35.3 of the Applied Analog Electronics textbook. There are two ways really to generate pulse width modulation signals. One of them uses a microcontroller or other computer to basically count out an amount of time for being high and count out an amount of time for being low in order to get a specified duty cycle. So if you're trying to control a motor, for example, and you want to say, I want this to be 75%, then you have the thing be high for 75 clock ticks and low for 25 clock ticks, or whatever the appropriate number of clock ticks is for getting the pulse width modulation frequency that you want. And this is the mechanism that gets used when you're doing things like motor control and stuff with a microcontroller. But we're looking here at a somewhat different problem where we have an audio input, an analog signal, and no computer involved. So we're looking for a simple analog trick, really, to get us the pulse width modulation from a analog signal. Let's take a look at how it works. It turns out not to be very difficult. We've got our slowly changing analog signal. And by slowly changing, I mean that the highest frequency involved in this analog signal is less than half our pulse width modulation frequency. And that's something that we need in order to be able to represent anything in discrete time. It's the Nyquist theorem. You can't represent frequencies higher than half your sampling frequency. What we're going to do is to create a triangle wave, and a triangle wave at the pulse width modulation frequency. So it goes up, comes down, goes up, comes down, goes up, and the frequency is the pulse width modulation frequency. What we're going to do is to compare the analog signal, that's the input signal there in black, with the triangle wave. Where the input signal is larger, we'll put out a high value. Where it's smaller, we'll put out a low value. What this does is give us our two values, high values and low values, as we wanted. And the duty cycle, the fraction of the time that signal is high, corresponds to the voltage on the analog signal. And the way that works is that, think about this now as being a very much lower frequency. So basically, as if the analog signal was constant. What fraction of the time will the signal be above the triangle wave? Well, if the signal is all the way here at the tip of the triangle wave, very top part, it'll always be above it. We'll have 100% of the time it's going to be above the signal. And if it's all the way down here at the bottom, 0% of the time will it be above the triangle wave. And so in between, because the triangle wave is spending an equal amount of time at every voltage, the percentage of the time that the signal will be above is precisely proportional to how far you are between 0% at the bottom and 100% at the top. So this gives us a duty cycle that is precisely proportional to what the voltage is between the low voltage and high voltage of the triangle wave. The pulse width modulation frequency is going to be just the frequency of this triangle wave, because we'll get one pulse for each triangle wave period. That's assuming, again, that our frequency of our signal is low enough that it's not fluctuating a lot during the period of of the triangle wave. The circuit for doing this is also extremely simple. We take a comparator. We have the analog input coming into the positive, and we have a triangle wave with the PWM frequency coming in the other input. And what comes out is a PWM signal. We do have to make sure that the range of this triangle wave, the voltage range for it from the low voltage to the high voltage, matches what we expect to see on the analog input. If the analog input goes above the peak of the PWM of the triangle wave here, then we're going to saturate at 100% duty cycle and we'll get clipping. Similarly, if the analog input drops below whatever the bottom voltage is for this triangle wave, we will get 0% duty cycle no matter how much below we are. And so again, we'll get clipping. So the analog input must always remain within the voltage range of the triangle wave. If the triangle wave has a huge voltage range compared to the analog input, then the duty cycle will only change a little bit. If the triangle wave has almost the same voltage range as the analog input, then the duty cycle will vary a lot. And we can take advantage of that to either get strong fluctuation in duty cycle or very small fluctuation in duty cycle, depending on what we need for our application. Generally, for what we'll be doing in the power amplifier, we'll want to have a fairly large variation in the duty cycle possible, because that will give us the largest variation in loudness of our signal out of the loudspeakers. But that may be too loud for a lot of applications, so for some of the times we'll be shrinking the analog input signal down to only a small piece of the voltage range of the triangle wave, getting a small fluctuation in duty cycle and a much quieter signal because of a smaller change in the effective signal to the loudspeaker. And that's really all there is to generating a PWM signal. We'll look in subsequent videos about how we can take this PWM signal and convert it into a large PWM signal to drive the loudspeakers, because what comes out of a comparator here is only a very small current. So we get a nice digital signal in terms of the voltage range, but small currents, so we can't drive anything like a loudspeaker with it. That's about it for generating PWM signals.